All right, as you guys can tell, our next speaker is going to be remote. Pleased to announce Allister Beharry. For my PhD, I actually created a programming language involving linear systems. So I'm very excited that he's going to provide a type-safe formulation for lots of linear algebra constructors. So, Allister, if you can hear us, go ahead and take over.
Yeah. Okay, I can hear you. Is the audio okay from me? Okay, cool. Okay, so good afternoon, everyone. My name is Allister, and I'm gonna present a little bit today on my project called Sylvester, which is a F# internal DSL for scientific computing. And part of what I'm doing at Sylvester involves using a lightweight or a structured form of dependent typing. Okay, so just a little bit about me. Not interesting, but I'm from Trinidad, West Indies. That's a very, very small island. It's very far away from the US. But we love programming here as well. I do open source development, mostly in .NET, also PHP, Ruby, Python. I started off, as most people doing mostly like object-oriented stuff, but eventually I basically started to fall in love with F#. I think it's a really, really cool. I mean, I'm still a beginner, but everything I learn about it is just like, make me want to do more and more with the language. I could not do something like Sylvester in, C# or another sort of object-oriented language. But also, I think that to me, it's very ironic that languages like Python now dominate scientific computing and machine learning, when Python is like the epitome of a sort of a procedural language with some object-oriented and functional stuff grafted on. Whereas, the Haskells and the OCamls and the F#s, they kind of pushed into a niche. Um, so what I would really like to see, I don't think I'm alone in this. I'd like to see basically functional languages like F#, but also Haskell, basically just sort of like carve that niche with them. Because really, that's what they were designed for. We should not have to be sort of like, out in the cool as far as like, and all the great stuff that's happening right now in machine learning. Yeah, so that's basically just a background about me and the project. So like I said, the project basically it's to create basically a language, not a separate language, but like an internal DSL inside F# for doing scientific computing. Both things like numeric computing, but also eventually symbolic computing. And basically, what makes Sylvester different from other languages is that I want to take the best bits of the functional programming and sort of apply it right now to basically to doing things like linear algebra, which is really, really important. And of course, we're just generally in scientific computing generally, but also in, well, a lot of it happening right now in machine learning. You think about things like word embeddings. Basically, the whole data science and machine learning stuff, basically, a lot of it is grounded on concepts of linear algebra, vector spaces, linear transformations, and things like that. So that's why I wanted to focus first on just that, but just that particular part about doing linear algebra. So I'm not going to so yeah, just gonna look at some of the goals of Sylvester, but I'm gonna switch now to Visual Studio Code. Okay, so I'll be switching back and forth because I would really like to show you basically this is actual code that's actually running. It's not just basically a prototype, even though it's still in development. This is basically something that you can use today. Let me clear some space. Okay, so this is basically well, I know there was a previous F# session from Philip, but mostly it's been for Compose this year. It's mostly been more like Haskell type languages, not many OCaml based languages. But I think you're already familiar about with ML. The ML family language. And F# is an ML family language. So the syntax is pretty, it should be pretty familiar to you. The first these are just references to the assemblies or libraries that Sylvester is going to use. Okay, and it's just saying, okay, I just want to open the Sylvester namespaces so I can bring the different functions and operators into scope. So, you guys basically know what's happening. So, okay, so I'm just going to go through basically some of the things that are implemented. So I can just, so basically, yeah, so I can basically just talk about sort of what the objectives are. So, okay, so the first part is here we have just declaring a vector. just a vector. And well, this IDE is Visual Studio Code with the Ironite extension, and it's a really, really terrific extension. Arguably it's the best F# IDE, and it's completely open source by volunteers. And it's actually, it actually has a lot of things, but there's a lot of things better than Microsoft's Visual Studio. So basically, when you declare a variable in F# in Visual Studio, you get basically you get the types. Okay, sorry, I forgot I was sharing the window. Sorry. Because the last time I tried to share the entire screen. Let me share my entire screen. Hopefully, minimize this so I don't go into infinite loop. Okay, should be. Yeah, okay, I think okay, you guys can see it now. Okay, cool. Okay, yeah, so this is Visual Studio Code. So I'm just. Oh, okay. I think maybe there's some lag. Yeah, are you seeing it now? Oh, okay. Oh, sorry, I had to click. Sorry. Yeah. Yeah. Okay. Yeah. Okay. Sorry about that. Okay. So this is the Visual Studio Code IDE, and basically here I'm just gonna basically. So I'm just saying I want to declare a vector of length 100, just initialize it with a constant value of 5. Now, if you can see what Visual Studio Code does, it basically prints the type right to the right of the variable declaration. So you can see that actually the type of this vector. So I can just hover over it and you can see type of the vector. The length of the vector, which is 100, it's 100 elements, is actually in as part of the type. Okay, and well, this is just so the second declaration, it's a vector, it's just a vector of 9,000 values, but has random values in it. And the other two declarations are just vectors of length 200 with just random values in it. Okay, so I can just go ahead and run this. Okay, so well, it's not very interesting, but you get the idea. Basically, it's a vector of values with these floating point values. Now, the interesting thing is that, well, first of all, as we saw, so you can see with these annotations that the ID puts to the side that the types of these vectors, the length is actually part of the type. So what that lets us do is, so okay, so I have the S1 variable. I'm saying give me a sum of the two vectors, and that's fine. Okay, I mean, so I'm just taking an element-wise sum of the values. Now, if I try, so I have I'm adding two vectors of length 200. Now, if I try to add a vector of length 200 and a vector of length 45, now you see what happens is that in Visual Studio Code, you get immediate feedback when the type checker gets into an error. You get immediate feedback. So you can see basically that the type checker has determined that what I'm typing is not a values of types. So I can just hover it on. Okay, sorry, I haven't defined my variable. It should be 100. Sorry. Yeah, okay, so I'm going to add a vector of 200 plus a vector of 100. Okay. Yeah, so let me get this so the ID can pick it up. Yeah, okay, thank you. Right, okay, here we go. So what you can see, the tool type, you have a type constraint mismatch because these two vectors, they aren't conformable for addition. Okay, they're different sizes. So I mean, that's really the basic idea. for using the sort of lightweight dependent type, because it's not full spectrum dependent typing, but it is a form of restricted lightweight typing where you can encode the numeric dimensions of the linear algebra objects into their type as part of the type expression. So basically, that's and I mean all of the examples are basically like this. So here we say, okay, I'm multiplying a vector by a scalar, and that's fine. I can take, but if I try to do, so the multiplication operation is defined as a cross product. So I can get the cross product of two vectors. So let's say I put in the other 200 length vector. Okay, so let's wait for the type checker to catch up with what we're doing. Right, so, and you can see that's the type checker is fine with this. And the result of this, this is the result is a scalar. Taking the dot product. But if I try to do it with a different size vector, okay, so trying to take the dot product. So again, you see the type checker determines that what I'm doing, the two types, they aren't conformable for multiplication. Right, so I mean, that is basically the heart of what I'm doing. So just talking about the goals of what I'm doing with Sylvester. So I'd like to have basically types for these linear algebra expressions, matrices and vectors, to have their numeric dimensions as part of their type. And because, well, as I said, we want to be able to create the instance of these vectors where have their dimension size as part of the expression. Um, you can see that there are different ways of creating it. You can either use the values, basically just use numeric values directly, or you can use a type constructor with the length of the vector or the length of the two matrix dimensions as part of the type. Okay, and this syntax is actually something that what's called a type providing visual in F sharp that lets you pass static parameters to a type. So this isn't like traditional F sharp syntax, but it is something that that type providers allow you to do. And I'll get into how Sylvester works with type providers all its own. Okay, so we saw basically where we were able to create these linear algebra expressions where the dimension is part of the type expression, and also we saw that we can have operator functions that are only defined for these expressions that are conformable. Okay, so and we can do another thing is we can do it for matrix things like matrix addition, and so okay, I'll get to this. I'll get back to this. And yeah, so just talking about the goals of what I want to do with Sylvester. Basically, right now for linear algebra, whether it's Python or Julia or C++ even, most of the checks as far as whether the operations that we're doing, they are actually making sense, they happen at runtime. Okay, so you actually have to run the code, and if you're lucky, you will get an error. If you're not lucky, you won't get an error, but the code will still be incorrect, and somebody is gonna wind up with a paycheck of $0 or something like that, down the line. So the idea is again focusing on safety because I mean machine learning is becoming so pervasive now in the justice system. I mean it's everywhere, and really it's becoming more and more important to be able to sort of catch these kind of errors before they make it to runtime. So this is so having these checks done at the type level, at compile time, at design time in the IDE. This is just basically part of how I can leverage some concept in functional programming, basically to make a better scientific computing language. Okay, and well, we saw basically that what we okay, so I can show this now. So here, this is another example. So this is a matrix. So I just created a matrix of it's 4 by 200. And so I'm just creating some matrices here, and you can see the types. Again, the types actually have the dimensions. The first two dimensions are actually in the type. And so this particular variable, it's not a square matrix. It's a non-square matrix. And what I can do is, so for instance, okay, let's say that I want to take the determinant. Well, we know that determinants only make sense for square matrices and also inverses. Now, if I were to put in my not square matrix, okay, so again, what happens is that the type checker is determining that this particular value is constrained to be equal to, so the dimension of the matrix of the two dimensions, they have to be equal. Okay, so here it's expecting that this matrix has a dimension of either, well, 700 by 700. But you can see basically that the constraint does not the constraint. So that particular matrix function has an invariant that says that basically whatever value it has to, the dimensions have to be the same size. And of course, this particular value violates those constraints. Okay, so I'll put this back just to make the type checker happy. And it's the same thing for taking an inverse. Um, if I put a not square matrix, it's going to tell me the same thing. Okay, so what we're trying to have on these natural number dimensions, where we can do this sort of type level arithmetic, and also type level constraints. And we want to do this in a way that it's not something that is external to what the user is doing. So you can see that as I'm in my IDE and I'm working, and the IDE is giving me back feedback on whether or not one of the types make sense. So when you compare something like this to what, for instance, C++ does, when you can have scalar values as part of some template parameter, but with this, that's just simply something happening when the compiler runs, and it has an assertion saying, okay, well, it's these type parameters don't know. But here, the types, they're actually an integrated part of the language, and the types are actually varying according to the values that are being put into the functions and operators. So um, I wanted to make that clear because, well, later on I'll talk about having, I know it's controversial to call what I'm doing here dependent typing. Of course, there's dependent type theory, which says that, the types, basically types can accept dynamic values, no matter what kind of values they are. And Sylvester does not do that. F sharp does not support, just does not support some. You can't have an arbitrary value as a parameter to a type. But I think that what Sylvester is doing, and we'll get into some more of what it can do later on, it goes beyond typical type level arithmetic that you would find in C++ and D and other languages. So that's why I think that it's sort of, it makes sense to call it a restricted form of dependent typing. And we'll get into the terminology and stuff all later on. Okay, so just talking some more about the goals of what I want to do with Sylvester. So I want to make something that, first of all, is tractable. Now, usually type level arithmetic, usually in functional languages, it's implemented using piano numbers. But piano numbers, once you get past a certain small values, it becomes really intractable for the type checker. And you can even, first time I tried piano numbers in F sharp, after I got to 4 extract. Because of the nature of how these numbers are constructed. Basically, the type checker has like an exponential problem as you just add 1, 1, 1. So I wanted to do something that would still be stable. And you can see that here that basically, even if I were to create like a really big value, like, okay, I can say something like, I don't know, 100,000 or something like that. Okay, and so if I were to use piano numbers to try to do this definitely would not work. But you can see that inside the IDE, the type checker, it's still tractable for the IDE, even though it's a relatively large number. So basically, the way that Sylvester, I'll get into this later on, so, but we're not using piano numbers for this because we want something that is actually tractable. without having to use any special induction type heuristics like what for instance type plus Scala, and different extensions to Haskell, that they have these flags or extensions where you can say, okay, well, I'm going to be using inductive type, so use these special heuristics. So, but this is just plain, well, I should mention, this is just plain vanilla F sharp, okay? This is just ordinary, there aren't any special extensions. We can run this actually inside IF sharp. So this is actually this is actually running on IF sharp notebook. This is a Jupyter notebook with an IF sharp kernel. And you can see we can do the same things that we're doing in the ID, we can do in Jupyter. So again, as far as the goals of Sylvester, so I wanted to be able to support basically having real world matrix and vector dimensions. And again, I don't want it to be brittle. I mean, there are like sort of like kind of techniques you can use to simulate dependent types. I think that's true in all functional languages, but it tends not to be like an integrated part of what you can do with the language, and that's not something. And Sylvester is something that it's not something that you have to hack. Okay, that's good. Okay, I think that's Google Hangouts somehow doesn't like what I'm doing with Visual Studio Code. Okay, let me switch back to the presentation. I'll get back to Visual Studio. So what we're saying is we don't want it to be brittle. We don't want it to rely on hacks. So any sort of like special techniques. We don't want to have to massage what we're doing. And so if you have existing code now, you can use Sylvester without having to do anything special with your code. And you saw there basically that it's just ordinary F sharp code. Again, it's just plain vanilla F sharp without any tooling or anything. And also, okay, let me just expand this. I think when I go full screen in Chrome, Visual Studio Code somehow complains about that. So I'm not sure what's happening, but basically, yeah, so just one of the points of being stable is that there are a lot of libraries coming out right now for numerical computing. There's math.net, which actually uses some native backends like Intel MKL or that you can use for numerical computing. And there are things like TensorFlow Sharp. There's things like Torch Sharp. I mean, it's really because of the rise of machine learning, you're having a really growing .NET ecosystem for numerical computing. And I would like to be able to bring this concept of dependent typing to make it to integrate into that ecosystem. And Sylvester actually right now uses actually math.net as the underlying numerical computing library. So we don't have to do anything special as far as like we're just using an ordinary numerical computing library and putting the strongly typed layer on top of it. Okay, so let's talk on some of the goals. Well, we saw that basically, the syntax is pretty much. I wonder if it's going to start. Okay, all right, it calmed down a little bit. If you guys aren't seeing this, just let me know, okay? So, and you can see with the syntax, it's very plain vanilla sort of vanilla syntax. We're not doing anything special or using any kind of like special syntax or we have to like a special constructor or anything. All this stuff would be familiar to any functional programmer. This would be really, really easy to understand. And all again, we want to be able to use Visual Studio Code and Visual Studio. So, to have that experience where as you're typing, the type checker can basically analyze the code and tell you what you're doing wrong. I think right now, as far as like machine learning, especially like if you're now starting off with machine learning and having to manipulate these multidimensional tensors, and things like that, that can be actually really, really useful to someone. Okay, and again, well, the way we're manipulating the types, it's very, very simple. We don't have to use any sort of like long constructors or anything like that. We also don't have to rely on compiler asserts. So I mean, F# does have this ability to assert things, but what we're doing is we're not really doing that sort of like compiler assertion. What we're doing is everything is within the F# type system. So we're not relying on anything external to what the user is going to be doing inside his or her environment. And also this thing about the return type. So let me switch back to Visual Studio Code. Okay, so okay, I'll switch it with Jupyter to show the spot. So with this particular one, so I'm taking, and I can use just any value really, it doesn't really matter. So I can say 300 plus 4 or something like that. Okay, so I have, again, I created a vector of size 200, and I'm trying to index into that vector, which of course on this index, and normally this error would only be caught at runtime, but because we're using Sylvester, and because the dimensions are part of the type, errors like these can actually be, okay, the reason it's saying this is because I didn't run the entire thing, but the basic idea, well, you can tell that the basic idea, which is that instead of having index out of range checks happening at runtime, you can have them happen at compile time. Okay, just run these cells again. Yeah, okay. So Jupyter has this, kind of unique way of using where you have to run the cells before you run the code. So again, so we can see here what we're doing with as far as like doing like with indices. So as long as I'm within the length of the vector is fine. But if I go out, and the thing about it is that the type that gets returned. So for instance, okay, we can look at this. The type is actually informative. It basically tells you, okay, well look, what you're doing is outside the range of the vector. Okay, so we're not returning a type that is opaque to what the operation the user is attempting to do. So again, we want it to be, okay, so still, okay, well, I mean, I think you sort of get the idea of what's happening. We want the type that's being returned to basically not be opaque, but to be able to give the user information as to what is actually going on. Okay, and well, again, I talked about this. I really would like to see F sharp be more, well, I mean, F sharp and Haskell and OCaml, all the different functional languages, but be used more in scientific computing and machine learning. I think there are a lot of benefits to be using these languages. But for F sharp in particular, it's functional first, but also it has these really powerful programming facilities. Well, we saw an example of a type provider, but also things like computation expressions. And I don't know if you're familiar with F sharp, but basically things that you can do. So, for instance, with NumPy. Okay, sorry. So time really went. Okay, so yeah, so basically the idea is we want to be able to use this meta programming so that you can write expressions and have them be evaluated by different, like, for example, by CUDA or by different numeric libraries. And that's something that you can do really, really well in F sharp with computation expressions. Okay, and of course, well, again, F sharp is built on .NET, which is, Microsoft's, that's their premier open source technology. I'm going to assume here that's a good thing. I guess you guys will feel differently. But there's a lot of tooling and libraries and environments for working with F sharp. Okay, and again, so I want this to be a practical mainstream idea of analytic programming and also just dependent typing in general, because there are a lot of languages like Idris, Agba, but they're more or less niche languages still. They're not utilizing not like sort of like the large scale mathematical computing machine learning. And just using these languages, to write, it can be a lot harder than using like say ML family language or a Haskell language. So that's why I think that F sharp can basically, something like F sharp can actually bring some of these benefits of dependent typing to scientific computing. And again, I think we saw how we can express these type level constraints without having to write any proofs of things that typically you would do in a language like Idris or ATS. Okay, and so just I guess the last thing I would talk about this idea of lightweight dependent typing. Well, we saw basically the idea, and so languages like Idris, Agba, ATS, these are for full spectrum dependent typing, and that's really, really cool. Everybody wants to have it. I mean, but it's actually really hard to do. So this idea of lightweight dependent typing, basically we just try to bring the safety benefits of the full spectrum dependent typing to a mainstream language. So it started off with languages like dependent ML, which is like a precursor to ATS. And yeah, so basically we want to bring this idea of like we want to bring these benefits of dependent typing to a mainstream language. And the only restriction is that, of course, that some information about these dimensions, they must be statically known. Okay, so okay, so Visual Studio Code is active. Whenever I go full screen, this is what happens. Yeah, so again, it's not full spectrum dependent typing. So basically we have to either, so for example, the name of the file containing the data, we have to have some sort of information about dimensions. So that's really the restriction. But I mean, in the scenario of mathematical computing, if you're doing machine learning, you have a fixed data set. You have like, for example, it's with image data. So you have a fixed. So I mean, in the context I was talking about, like training machine models, doing scientific computing, that's not necessarily, a downside. Most of the code you would look at, you would see where they create, for example, they create a 5x5 matrix for convolutions. And no one is doing the sort of like having dynamic values in their matrices. Okay, it's not really that common right now. So that's not really a big downside. Yes. So I think probably my time is almost up. Yeah. So just one last thing, I just want to talk about. Oh, of course, my idea is going to go crazy again. Okay, so yeah, I think I covered a lot of what Sylvester can do. So here we're just seeing some matrix operations. We can do column level. Again, we see that with non-conformal matrices, you can't multiply them. You get a type mismatch error. And we can do column level operations. So I mean, I think I gave a basic idea of what Sylvester is trying to do. And so, I mean, this is my first really major functional programming project, and I'm really enjoying it. And I really hope that this can go on to be something that is really widely used in machine learning. And so okay, that's it. Thank you very much.